You're listening to the Wurth Electronics What's Up radio podcast, where each week we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Wurth Electronic technical specialists who are going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Electronics What's Up podcast. Zero insertion force, commonly known as ZIF, and flat flexible cable, or FFC connectors, are extensively used in data PCBs. But there's currently no standard that precisely defines the signal integrity characteristics of these connectors as characteristic impedance, S parameters, and available protocols. So the aim of this podcast is to emphasize the importance of prioritizing signal integrity principles and to explain which frequencies can successfully pass through these connectors. We'll also discuss influential factors like FFC length, pitch, and connector type. Additionally, we're going to explore some real-world use cases, such as the effects of bending an FFC and the consequences of contact with an FFC. Plus, we'll be addressing some common questions that engineers may be overlooking.
And today we will speak about ZIF and FFC signal integrity. So ZIF and FFC is a very, very common connector that you use a lot, that everyone uses a lot since long years now. And you use it not for power, of course, but for signal. And in most of the datasheets, you will not really find the information of what kind of protocols you are able to use with it, what is the bandwidth, what is the impedance, all that information that should be necessary to properly use a signal connector. The reason is that this is not standardized. Really, you will not find any standard that define precisely the rules on how to define it, on how to define the frequency, the bandwidth, all that interesting information. Of course, you know it for the USB, for the HDMI, for the modular jack connectors, because this is clearly defined in the standard. That's not the case here, and that's one of the reasons why this is hard to find this kind of information. Today, you will learn more about our ZIF and FFC products. But first, we will have a look on some impedance and S parameters reminders. Of course, so one thing that is very basic is that the EM wave, electromagnetic wave that is traveling in your PCB is the same than the light. The light is an EM wave exactly the same that is traveling in your PCB. That's important to understand. Just the frequency change, but that's exactly the same phenomena. And so this is quite easy to understand how it works, because on a PCB, this is complex. It seems complex, but in the real life, everyone knows about the light. And for example, here, this is a picture that I took from our building here. Here you have a painting where you see the Wurth Elektronik logo, and in the background some of our skyscraper that we have in the city, small skyscrapers. This is not New York. So if you are here and you look for the painting, then you see the light that is traveling in the air without any change, because this is just the air. You don't change the medium where you EM wave, so the light is traveling. So what you see is completely the painting. Okay, everybody knows that. But if you see here, there is a sound box, and if when the light touch the window that you can see here, then you will change the medium where the light is traveling, where the EM wave is traveling. And so when you change the medium, then you will have a reflection here. Of course, everyone knows that. This is the picture here. This is me that is taking the picture, and you can see the painting that is here. This is a reflection. This is obvious. this is because you have an impedance change. This is called an impedance mismatch. This is the characteristic impedance. And so, imagine now you are in the box. So what you will receive when you are inside of the box is the initial signal from the painting that is traveling here, minus the reflection power of the signal, and minus the absorption of the window that is, of the glass that is here. Because as you can see, the glass is a little bit smoked, so the light will be a little bit absorbed by the signal, by the smoked glass. And so what you will see at the end is the painting, yes, but minus the power reflected and minus the power absorbed. So for the signal entirety, we call that reflection loss or return loss. This is called S11, 1 because this is where the signal is sent and the signal is measured, 1, and S21, as you can see, is called insertion loss because this is sent from 1 and measured on 2. Quite easy. But of course, that's not the topic of today. The topic is signal entirety. So we go back to the PCB. You will see that's exactly the same phenomena. You've got your signal trace here. You've got the ground here and the ground here. That's a coplanar trace. And you've got the ground on the bottom layer. Of course, this is very, very simple PCB. This is not the real life, I know, but this is just to make you understand. When you send a voltage and a current or signal inside of the trace, then you will create an electric field between the ground and the signal here, from here to here, from here to here, and from here to here. And of course, you will have the magnetic field also. So electric field plus magnetic field, this is an EM field. And what is also really important to understand is that what is important here is not the current and the voltage that is traveling inside of the copper, but really what is out of the signal. Your power, the power of your signal is not inside of the copper, but outside of the copper through the EM field. And so what is really important is not the copper trace, but what is out of the copper trace. For example, the material that you use for your PCB, FR4 or not, and the distance that you will find between the trace and the ground layer. This is symbolized by a parameter that is called characteristic impedance. And at high frequency, well, we don't have the time to develop how to get that equation. I've got only one equation during this presentation. This is this one. At high frequency, the characteristic impedance is roughly equal to the square root of the inductance divided by the capacitance. And how is characterized the capacitance? You will see why I say that. This is to have a better feeling and understanding of your characteristic impedance. Because, for example, here, the capacitance is linked to the distance between the trace and the ground, is linked to the distance between the trace and this bottom ground layer, is linked to the permittivity of, let's say, the FR4 or the PCB material you use, the width. For example, if you increase the width, this parameter, then that will increase the capacitance. And so if you increase the capacitance, you will decrease the characteristic impedance. If you increase the 8 here, this distance, then you will decrease the capacitance and then you will increase the characteristic impedance. Okay. That gives you good information on the best way to feel this characteristic impedance. But of course, if you want to really have a real good characteristic impedance calculation, then you need more. You have characteristic impedance calculation everywhere on internet, on Altium. This is here how I did to create a 50 ohm trace. Then this is a thickness of 35 micrometer, classical, with 1.2 clearance of 0.25 on the PCB of 1.6. And now we go to the setup. the setup is what I say here. This is the PCB I use to do all the measurements. Here you see we recognize a ZIF from our brand, of course. 2 traces of 50 ohms, so for differential pair, this is 50 plus 50, 100 ohm. You see you have a lot of vias that links the top and ground bottom there, and via stitching all along the trace that are here. And today we have only 30 minutes to present you that, so we will talk only about differential pair. But of course, if you want, we have all information on the single end. So here today we will see ground, single, single, ground. So single, single is a differential pair. One small reminder about the decibel. That's important because we always talk about decibel, dB, and well, even me, sometimes I forget what it means. So below minus 20 for the return loss, this is below of 1% of the power reflected. Between minus 20 and minus 10 dB, you've got below 10% of the power reflected, and above, this is of course above 10%. So of course it depends on your application, depends on your protocol, but let's consider for this training that very good is below 1% and acceptable is below 10% of the power reflected. For S21, yeah, this is written DD here because this is a differential pair. So for the insertion loss, this is easier because you know the concept of bandwidth. The bandwidth is minus 3 dB. It means that this is below 50% of the signal loss for the insertion loss. So now we go a little bit more into the topic. What we want to know is what is possible to put as frequency and impedance inside of our connector. Regarding the pitch also, we have the pitch of 1, the pitch of 0.5, what is the influence of the right angle with the horizontal one, what is the influence of the leaf and the ZIF, is it better? Some interesting parameter. We have tin and gold contact for ZIF and FFC. Who is the best? If you take gold contact, will it increase the signal integrity or not? You don't know, maybe you will have the answer. What is the influence of FFC length? And if we, because we have also folded cables, so does it has an influence? Does it decrease the signal integrity or not? That is also an interesting question that I have had a lot of time in the past. So I hope you will learn it today. So, last thing before we go into the figures, then how the measurement are done. We use a VNA Rode-Schwarz here, 4 ports, and you send different per signal here, and you do the measurement here. And what you see here is that for the impedance, you send a signal. This is 100 ohm because this is here the measurement of the coax cable, 50 plus 50, this is 100 ohm. Here you've got the connection of the solderless SMA. You see that there is a small impedance change. This is not really, these are good connectors, but this is not possible to have strictly no impedance mismatch here, simply because you are in a perfect coax round, and here you go in a more 2D, 2 dimensions medium. So you have a change in the geometry, so in the capacitance, so in the characteristic impedance. And also here you have the PCB traces that are not purely 50 ohm, well 100 ohm in that case, due to the FR4, the glass fiber, to different some kind of parameters that you cannot avoid. But here only you have the ZIF impedance, and here the FFC characteristic impedance. You can see that the characteristic impedance decline in the time. It does not mean that the impedance is not stable, because it is stable, But if you send a signal power here, then each time you have an impedance change, then you will have a return loss. So the power of the initial signal decrease in the time. So the reflected power will naturally decrease also. So what you see here is the impedance decrease, but the characteristic impedance is stable all along the FFC. That said, so first we have this measurement. The ZIF of pitch of 1 is roughly equal to 77 ohm, and the FFC is roughly equal the pitch of 1 to 120 ohm. Just to give you a reminder, USB protocol needs 90 ohm and Ethernet protocol needs 100 ohm. So here you see that this is not purely what you're looking for. If you use USB or Ethernet, you have an impedance mismatch, so you will have a return loss. You will not have a perfect insertion loss. You know it with that curve, but what is the real importance of that reflection and insertion loss? You know with that curve. This is the return loss. Here is the frequency in megahertz. So up to 20 gigahertz. 20 gigahertz is really too much for that connector. Of course, this is the return loss. And so here, let's consider the 50 millimeter, because here this is the FFC length. At 50 millimeter, you reach minus 20 dB at 800 megahertz, which is really, really high in terms of frequency. But if you increase the length of the FFC, then you will see that at minus 20 dB, for example, for the longest one, 500 millimeter, then you have only 30 megahertz. So what you see is that if you want to limit the return loss, then you need to shorten your FFC. Obviously, that's the same for the insertion loss. This is the same scale, insertion loss in decibel here. Minus 3 dB, you see that for the 50 millimeter, you've got a bandwidth at 3.5 gigahertz, which is really, really high. And at 500 millimeter, you've got a bandwidth at 700 megahertz, which is also really high. So you can really work with the ZIF and the FFC. And of course, the signal integrity will decrease when you increase the FFC length. Okay, now what is the influence of the pitch? You've got two curves of the impedance. The first one is for the pitch of 0.5. Second one is the pitch of 1 millimeter. You see that the impedance is really, really close, and the return loss here, orange and blue, and the insertion loss are really close. So the conclusion is easy. This is the same. So you choose the pitch of your ZIF for your application for mechanical, I don't know what kind of reason, but that's not a topic for the signal integrity, because that gives the same good results. Now, an interesting question that I repeated, but I had a lot of time in the past. So what is the influence between a flat FFC and a folded FFC? We have in our range 200 millimeter flat and 200 millimeter folded. Is it better? I let you have your own opinion. Oh my God, not so much. Well, not really actually. Flat and folded gives more or less the same impedance. So normally we should not have so much difference in the return loss and insertion loss. And that is what happens. So return loss and insertion loss are more or less the same. So the answer is clearly the flat and the folded does not give any influence on the signal integrity. So do not be scared to use a folded FFC. And now an interesting question also. We have in the range also gold and tin plating for FFC and ZIF. So, of course, all of you knows that this is better to use gold for data. But do you really know why this is so important? Because we have gold everywhere. I mean, we have gold on the USB Type-C connector. We have gold on the modular jack, on the HDMI, a lot of different kind of thing for data. But what is the real reason for that? Because of course, gold is more expensive than the tin. That's completely obvious. And that's the case for every brand, of course. Does it bring something to the signal integrity? That's strange. What we see here is that the impedance is the same for tin and gold. So we'll see, does it have an influence on the return loss and insertion loss? Not at all. This is exactly the same. So I am wondering, why do we have to buy gold instead of tin, then use tin? This is a good question. And the answer is, don't forget that this is done with new products, and with new products, you have no oxidation issue. The big advantage of gold is that you cannot corrode gold ever. Apart from some specific chemicals, but that's really too specific. You cannot corrode gold with salt, with humidity, with pollution, with anything you want. And that will never happen, not in 6 months, never, never. And that's also increase the number of mating cycles you can use it. So in that case, what you have at the beginning, you will have in 6 months, you will have in 5 years, 10 years, 20 years, whatever you want. Tin is more sensible to oxidation, and any kind of metal oxidation will increase the contact resistance, and so will decrease the signal integrity. But of course, that does not mean that you cannot use tin for data. You can use ZIF and FFC tin if you are in a closed box, if you don't, without any too much dust, standard moisture, and if you do not touch the FFC every day with your hand, because on your hand, you always have grease, pollution, because you touch everything. And so you will bring chemicals on the product that will oxidate your plating. So that will do strictly nothing on gold, and that will oxidate the tin. So if you want that your contact is usable with your hands, if you want to have a, not, let's say, a harsh environment or a lot of moisture, pollution, which is outside, then you have to use gold. Now the eye diagram. We know now above which kind of, up to what kind of frequency we can use our product. But sometimes you have the question, I want to use USB 2.0 for my ZIF. Is it possible? Yes or not? We can do this on the VNA. You can do a high diagram that is called like this. So you send a lot of bits, falling edge, rising edge, falling edge, and you have the printing of each bit one after the other. And a lot of bits are printed here. You have the eye mask that is given by the standards, and if the eye mask is integrated inside of the eye diagram is deformed, of course, by all the parasitic capacitance, inductance, all the circuit. Then if it's inside, then you can say, yes, the USB 2.0 could be used for FFC and ZIF. USB 3.2, that's yes, up to 200 millimeters folded or not, but above this is a little bit too much. And 3.2 Gen 2, this is not possible, this is too fast. So this is the answer, yes or not. And now, fun facts, that's how I call these parts. This is, I would say, more applicable things, influence on different parameters, because of course the FFC is not fully in the air. It will touch the table. It will touch your cabinet in metal. It will touch something. I don't know what. So I try to do some interesting parameters. For example, here I put a scissors on the FFC. And you will tell me, but okay, it does not touch the copper, so it has no influence. No, remember that what is more important is not the copper trace. The copper is just the waveguide. And what is important, the power of your signal is out of the trace here. And so if you put a metal scissors, a steel scissors, on the FFC, then the wave will go inside of the scissors. So it will have an influence on the characteristic impedance. Here, you obviously see that you have a big influence of this parameter. This is orange, this is this one, in blue, this is this one. But so we now know that you have an influence, but it has an influence on the return loss and the insertion loss? Yes, above 1 gigahertz. So above 1 gigahertz, you will decrease faster your signal integrity and you will increase a lot, too much, your return loss. Okay, above 1 gigahertz. If you want to use it, then you do not have to put the scissors, but you will see there is another example that is really interesting also just afterwards. You do not want, I don't know, you have vibrations on your system, then you don't want to the FFC that is moving up and down always, then you take Kapton, this is a Kapton tape here, any kind of tape, and you stick it. That I did it on the table. This is a plastic wood table. Does it have an influence on the signal integrity? Yes, you see that the impedance change. You have an impedance change because you change the permittivity of the environment of the signal. Does it have an impact? Not really, not really. So you do not have really to consider that. The insertion loss is a little bit different, but not so much. So if you do not want that your FFC is moving up and down, then you can do it. But if you do it on a metal plate, like a cabinet, metal box that is linked to the ground, does it have an influence? Of course, yes. You really have a big impedance mismatch here. And what is the influence on the return and insertion loss is that the same above 1 gigahertz, this is comparable to the scissors. So above 1 gigahertz, it will change your signal integrity. You will decrease really fast your insertion loss and you will increase a lot the return loss. One thing is a little bit funny is that you will improve below 1 gigahertz, you will improve your return loss if you stick it to a metal box, and you will not really change your signal, your insertion loss. Of course, you will not take in your hands all along the product life the FFC. That's okay. But imagine that you are doing tests and because you don't want that it's dropping down, then you take with your hands the FFC and you do your test, and that's not really working. Maybe that's working in the real life. We'll see what's the influence. You see the influence is that you have a big impedance mismatch. And in that case, you have a big influence on the insertion loss. You see that above 100 megahertz, you will decrease very fast your insertion loss. And so if you do a test on your system, do not take the FFC in your hands, because you see that it will not really kill your signal, but it will change your signal due to the permittivity, to the contact with the ground, due to a lot of factors. And the last fun fact I have is a question that I have a lot, is that we know that the folded FFC does not have any impact, but questions from the customer are often, I want to bend the FFC by my own because I have specific directions to take because of my mechanical configuration. Can I do that? Will I kill my signal or not? Then I did 280 degrees bending here with my hand. And I can tell you that I really did with sharp edge pushing like this. So this is a real sharp edge bending. Does it have an influence? No on the impedance and no on the return and insertion loss. So the answer, I may be able to do that. Yes, without any fear, because you will not change your signal integrity. At the end, we know that the pitch of 0.5 and 1 millimeter gives good results, depending on the FFC length, of course, up to 3.5 for the bandwidth, gigahertz for the bandwidth, for smallest FFC. Parameters with low sensitive relative impact, the ZIF and the LIF are the same. Gold plating and tin gives the same result in the beginning, but if you want to use it and to manipulate it and to do a lot of mating cycles, then use gold. ZIF vertical has no difference with the horizontal. The FFC stick on the table, on the standard table, and the FFC folded has no impact or low impact on the signal integrity. What changed a little bit is that if you stick it on a round metal table, if you touch it with your hand, if your FFC is in contact with a metal part, with the insulator of the FFC, not the copper trace inside of the FFC. And of course, what has a high impact on signal integrity is the FFC length. This is, the connector is quite small. And what is important is to limit the impedance mismatch for a long time. So long cables is an issue for the signal integrity. A USB IDRAM, USB 2.0 is okay. USB 3.2 Gen 1 is okay up to 200 millimeters. And Gen 2 is not possible.
Make sure you check out the lineup of ZIF and FFC connectors, as well as input, output, circular, coaxial, and LED connectors, all available at Wurth Elektronik online. There, you'll also find terminal blocks, DC power jacks, and a full connectors design kit. Visit www.we-online.com to learn more, and for any questions you might have, click on the icon to talk with our live chat team. While the video and images are shown on most podcast streaming networks, we understand that the video is unavailable for some platforms. So to view the materials and replay that video on demand, check out the Wurth Elektronik YouTube page. You're listening to Wurth Elektronik's What's Up Radio podcast, where each week we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Elektronik technical specialists who are going to shine a light on interesting topics, like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Wurth Elektronik's What's Up podcast.